Hi everyone, Asha this side. In this video, I will tell you the project I built in my internship of Emertex. This project is all about the EV ADAS dashboard, a real-time electric vehicle monitoring and advanced driver assistance system, which is built on STM32 and simulated in PixSimLab and visualized on a Python dashboard over UI. This is all about the slide 1. And this second slide is content about what is the main agenda of this project. First is the project objective and the system architecture. Second is the hardware and tools, what the hardware and tools are used in this in this project. Third is EV parameter monitoring. Fourth is ADAS safety features. What is the safety features I included in this project? Fifth is the UART communication, and sixth is the fault and alarm system. Third one is what is the objective of this project? Is the goal was to build an end-to-end embedded system that is a real AV's instrument cluster and ADAS safety layer. Since this is the online internship, we do the realistic AV sensor behavior simulates on PixSimLab instead of the physical hardware. And the STM32, this STM32 is an ARM or Cortex CM3 microcontroller, which is read that simulated sensor data and compute vehicle parameters like speed, torque, state of charge, and range. And this data is streamed over UART at 11,5200 bit per second to a Python. Telling about the dashboard which is visualize everything live. So why we use STM32 specifically? It is because it builds an ARM Cortex M architecture, which is an industry standard, which is most embedded and automotive controllers to do are ARM based. So this experience carries over directly to our real industries. So fourth slide is containing about the full data flow. What is the system architecture about the full data flow? It containing this side. So first is the project simulated. So on the Pixim Lab, which project simulated on the Pixim Lab. So which is define speed, battery, temperature, and ultrasonic inputs, and then this feed into the STM32 blueprint. So then that firmware reads these sensors, computes system on chip, torque, range, and fault logic. Then stream structure data over UART at 11,5200 bit per second to the Python dashboard, which is handled live in visualization and blind spot alone. Fifth slide containing the hardware and tools. What is the hardware and tools we using in this project? So first is the STM32 blueprint. It is which runs actually firmware. It was reading sensors, doing math calculation, and managing fault. Second is a PiximLab. PiximLab is the circuit and peripheral simulator that emulates all EV sensor input without needing physical hardware. Third is a Python dashboard. Python dashboard is a custom desktop application I built for live plotting of vehicle metrics and alerts. Fourth is a UART. UART at the 11,5200 bit per second is the serial link connectivity, the firmware to the dashboard. So there are two concepts that I learned during this internship. Is the first one is the ADC. ADC is the analog to digital converter. It simulated sensors output at analog voltage, and the STM32 can only process digital values. So 12-bit at ADC converter voltage into usable number. So ADC converts the voltage into the usable number. Second one is the hardware timers. Instead of using simple delay functions that would freeze voltage program, I use timer interrupt so sensor reads happen on an exact non-block schedule. Six slide is contain Sixth slide is contain the real-time EV parameter monitor. So there are five parameters that are tracked continuously. First is a speed. It is a derived from sensor pulses. Second is a battery SoC means system on chip. It is a tracked as a percentage. Third is a motor temperature. The temperature monitor for overheating risk. Fourth is a torque. It is a calculated from load and motor parameter. Fifth is a range estimative. It is a predicted from SOC uses. So slide 7 is okay. Slide 7 is giving the ADAS safety features. There are three safety features. First is a forward collision warning, which detects closing distance to obstacle ahead and raises an early alert. Second is a blind spot detection, which monitors zones outside the driver's view. Third is a parking assist, giving proximity feedback in tight spaces. Slide 8 contains the UR communication. Oh, how the UR communicate. The link between firmware and dashboard works in three steps. First is a firmware package reading. It does the STM32 package speed, SOC temperature, torque, range, and fault flag into structured data frame. Second is a serial communication, which is data transmit continuously over UART at 11,5200 bits per second. Third is a dashboard. If it is a Python, that is application reads that serial stream, passes each field and updates the dashboard line. Telling about UART, it is a universal asynchronous receiver transmitter. It is a simple two-wire protocol. What is the slide 9? Slide 9 is alarm and fault detection system. It is there are four faulted conditions are continuously checked over the system. So first is a over temperature fault, which motor's temperature crossing a safe threshold triggers a warning on the dashboard. Second one is a low battery alert. Third one is a FCW. FCW is a forward collision warning, and fourth one is a communication fault. The next slide is a Python dashboard visualization. Dashboard visualization. This dashboard contain the numeric gauges for speed, stem on chip, temperature, range, and a live train plot for torque, and color coded alert banners for forward collision warning, blind spot, and fault condition. All this referred continuously from the 11,5200 bits per second in serial stream. So I will show these all live movements. So first of all, the STM32 ID. This one is the main .c uh, .c file. Here is the firmware structure of this project. The file of name main.c handles the initialization um, and the main loop. I will give you the build format. There are no any errors or there are so build the project. So building the project here. So yeah, there is a zero error, zero warning. So next one is a Pixim Lab. Pixim Lab, there are this is the board we using here, and this was the main. Yeah, there are four. Oh, this is a blue pill board. Uh, yeah, this one is the blue pill board, and this four potentiometer. There are four potentiometer here that is simulating the accelerating pedal, brake pedal, battery system on chip, and motor temperature. And this is our three ultrasonic sensors simulate front, left, and right distance detecting for ADAS system. And this LED is indicated collision. This LED indicating the collision and the blind spot on the other side. So there are dashboard I have you do For the dashboard, uh, um, I give the code for the dashboard. So here is the code for the dashboard, Python code, and there here is the all the um, dashboard. Yeah, the dashboard contain the speed gauge responding to accelerated, the system on chip and range quite updating together. There are line torques responding to pedal input. There are forward collision warning alert um, and appearing when the front distance drop. The blind spot banner appearing on the corresponding side. So yeah, uh, this is one is the dashboard. There are speed increasing and coming. They will track the all the forward direction collision and all of this. Yeah, this was the normal mode. Yeah, this was the normal mode. The next is the um, yeah, this was my files I have created for this project. Every file I have created for the project. So yeah, the uh, the 11th slide is all about the quick recap of all this project. What is this? What component I used in this project. So their component uses this STM32 firmware for the firmware development, the real-time monitoring dashboard I have created, the Python-based live visualization, the UART communication at 11,500 bits per second, and there are four collision warning, blind spot detection, battery system on chip and range estimation, motor temperature monitoring, and the alarm fault detection. So that is the EV ADAS dashboard. So thank you for watching. And if you have any questions, tell me in the comments. Bye, bye, bye. See you later.